definition, it's clear that you should be able to get whatever dimension you want, a wide range of open book decompositions. In fact, quite a bit more is true, just looking generally at the existence question of these things. So most of what I'm writing here is due to Quinn in 78, other than one small little thing that I'll mention. So Quinn tells us that, in fact, if I'm looking at an odd dimensional manifold, where n here should be at least 1, I guess, always has an open book decomposition. So we should point out here that dimension 3 was already known due to Alexander in the 20s, the 1920s. So that's an old classical result. Quinn's work is more an algebraic topological result. It works in dimension 5 and above. He also tells us that as long as n is greater than 2, has an open book, if and only if some invariant he cooked up, which later got named the asymmetric signature, vanishes. If you know what the usual signature is, it's very similar to that. But this turns out to be an if and only if statement. Maybe another M asymmetric. So in any event, algebraic topology knows all about it. The classification's all done. It's classic in a sense, except for the case N4, which interestingly is still open. So sort of this usual phenomenon of higher dimensional things being governed largely by algebraic topology, three-dimensional things requiring some sort of ad hoc argument, and dimension 4 just causing a big mess. I did do a bit of looking around, and apparently, at least according to Math Overflow, some people are thinking about this. So you can go and look at that if you're interested. Not really the focus of this talk, but I thought it was worth, for completeness, just having it up there. So open books sort of show up all over the place. I thought I would highlight a few places where you might have seen them in other contexts. Of course, fibered knots. Fairly commonly studied thing in low-dimensional topology. This is just the case that M is S3. They also show up in the context of Milnor fibers. Which you might be more familiar with. So the basic idea here, if we look at sort of the simplest example of this, what do we have? We want some complex, say a polynomial, mapping some high dimension complex of space into regular complex space, and it takes the origin to the origin, and perhaps it has some isolated critical point at 0. Well, then we just do the standard thing. We look at the associated link. So we take f inverse of 0, and we intersect it with some little sphere, which in this case should be a unit sphere of S2n minus 1. I think so. So this should be sort of small enough that it only contains our critical point. And then what Milnor tells us is that this is the binding of an open book decomposition of S2n minus 1 with the fibration given by just the argument of the map. So this gives you sort of interesting open book decompositions of spheres of any dimension, where by interesting I mean having sort of non-trivial monodromy. The last example I want to look at, though, and I want to look at in a little bit more detail because it pushes us in the direction that I want to go, is that of the boundary of a Lefschetz fibration. vibration, particularly a Lefschetz vibration of a 4 manifold with boundary, sometimes referred to as a bounded Lefschetz vibration. And in a few minutes, I'll tell you why I want to restrict to 4 dimensions, but just bear with me for now. So what is this? So what we should have is some map from a 4 manifold. So I'll say W4, and this one will have boundary. And so I'm considering that there's some map G, smooth map from my manifold down onto the 2 disk, and it should have the property that near each critical point, I can find complex coordinates such that what this is doing is just taking my arguments, Z1, Z2, and spitting out Z1 squared plus Z2 squared. So it's a fairly specific condition on this. So Lefschetz vibrations, if you haven't run into them before, they are known in particular to determine Stein domains. So there's a type of complex manifold that has a boundary that's very useful in these types of constructions. And we'll get to the geometric side of it in a minute. But for now, I just want to look at the topology of this thing. And the way we should, if I draw over here, it should be okay, right? So what are we doing? We're looking, we have a D2 and some total space above it. If I look at a regular value of my function, well, sitting over it, I should have some surface with boundary. And if I look over a critical value, well, I'll have a surface that's singular in some sense. It'll be crushed down to a point at some point. I don't really care too much about that at the moment. But what I'd note is if I go home and do the exercise and look at what this force is on me, and I consider a little circle of regular values around my critical value, I'll see that above that, I have a surface bundle whose monodromy is given by a single positive Den twist. So this just means, if you've not seen a Den twist, I take a curve in my surface, a closed curve, I cut along that curve, I glue it, I twist it 360 degrees, and glue it back together. So the Den twist will show up a bunch of times in the talk, so it's worth understanding. So of course I could have more than one critical value. I push over all those critical values, and I end up on over the boundary of D2, having now a surface bundle with the property that I can factorize its monodromy into a bunch of Den twists. That's sort of the main thing that we want to get out of this. But let's look at what that boundary looks like. So here, the boundary of W, I can decompose it as the bundle I just talked about. So that's, what did I call this, G? G inverse of the boundary of D2. But that's not all, right? Because I also have the boundary coming from the boundary of the surface across what's downstairs. So let's call this surface something. We'll call it S. Boundary of S across D2. So again, exactly the data of an open book decomposition. So again, this is the point at the talk at which we start to move into sort of a different focus, not looking at an open book decomposition as something that determines a smooth manifold, but something that in fact encodes some geometric structure on that manifold. So it should have a secondary purpose. So let me step back a little bit, draw sort of a big picture of the type of objects we're going to be interested in, and then get back to talking about the open books once I've done that. Generally happy with things? Good. Okay, so what's our general picture? So the general picture that we're sort of thinking of is this study of smooth manifolds, particularly 4 manifolds. Again, I'll say why I like those more than other manifolds. And the study starting in the 80s with Gromov's work on pseudo-holomorphic curves. So you're looking at maps of Riemann surfaces into these manifolds, and you want them to satisfy the pseudo-holomorphic condition. To do so, of course, you need more than just a smooth structure on your 4 manifold. You need an almost complex structure. So this is just a regular complex structure on each tangent space. It should sort of smoothly vary, but it doesn't necessarily come from a complex atlas. So this could be more generally a symplectic manifold, this sort of thing. And so in this context, one is generally interested in trying to port over tools that are more common from smooth manifold topology, in particular the idea that we can break it up into pieces, understand the pieces, glue them all back together. So to do this, we need to understand a little bit about what's happening on the boundary of the pieces that we break off. And it turns out that the sort of the correct structure to keep track of here to allow us to extend our geometric structures over these gluing constructions is what's known, well, not what's known as, is what is the complex tangency field. So the field of the plane field in the tangent bundle that I get by looking at the tangent space of the three manifold, and then I hit it with my almost complex structure J. I take their intersection. I'll get a plane at each point, so I now have some smoothly varying plane field. And this is an example of what's known as a contact structure. So just for completeness, even though the point of the talk is to sort of push the heavy lifting over onto the open book decompositions, let's just define what it means to be a contact structure. They will be denoted by the Greek letter xi, and they are determined by, i.e., xi is the kernel of some one form, which we'll call alpha. So alpha is some globally defined, I called it M, yeah. And it has this nowhere integrable condition. So it's sort of the opposite of a foliation. Haven't seen such a thing. So contact structures are kind of the auxiliary data that we want to keep track of throughout this. And this is where open book decompositions come back into it, because open book decompositions are sort of uniquely, in some sense, able to record contact structures in a way that I'll explain now. So let's see, does this fit here without falling? That's pretty good. Okay, where was I? So just a little bit of history here. So in 1975, Thurston and Winkelnkemper worked out that given an open book decomposition of a three manifold, which of course we knew exists by Alexander, as long as we're in dimension 3 back in 75. Quinn hadn't done his stuff yet. But we could cook up a contact structure. So just notationally, if we start with the data of an open book, so I have some page S, I have some monodromy phi. What I'm going to get over here, I will call C sub phi. So this is the contact structure supported by this open book decomposition. For the curious, the construction creates a contact structure with the following properties. If I have alpha defining one form, like over there, for my contact structure C, it's defining one form, or A defining one form, should be such that D of it should be an area form on the pages, and the form itself should be positive on the binding. And if your intuition for such things isn't very good, the way we should think about this is that the contact plane field should be nearly tangent as you go along the pages. When you get towards the binding, it should kind of twist, be transverse to the binding, then go back to being nearly tangent to the pages. And so within the class of things that do that, you come up with one that's properly contact. So this in particular showed that every three manifold has a contact structure. turns out much, much more is true, and Giroux formalized all of this somewhat famously in a speech here in Beijing, actually, in 2002, in the ICM of that year. So let's say 02. And establishing a one-to-one correspondence between open book decompositions on a given three-manifold M. I should put 3 here. Well, up to, importantly, a stabilization operation that I'll describe in a bit, and contact structures on my manifold up to contact isotopy. So in some sense, they really are exactly the same thing, a contact structure and this equivalence class of open book decompositions. We would be remiss here if we did not point out that, I guess when Giroux first announced this, some details were forthcoming. They never came forth. But he also had sort of established a larger multi-dimensional conjectural version of this, all of which was put together and proved just last year. So Breen, Honda, and Huang in 2024 proved this as part of a larger extension to higher dimensions. And this is a point at which I should probably say something about why we're focusing on dimension 3. I should also get a sip of water. Let me do that. I should probably also be writing a bit larger, so I'll try to do that. So anyways, there's an extension of Giroux's theorem to higher dimensions. The problem with the extension to higher dimensions is that it's not nearly as clean in higher dimensions as it is in 3 dimensions. In some sense, I guess, reflecting the way the categories, smooth, topological, symplectic, diverge, the larger your dimension is. So when I make this statement in higher dimensions, I have to put all sorts of geometric conditions on my open book decompositions. Their pages need to be symplectic. The maps involved have to be symplectomorphisms, even more. So in the larger sense, when I make these sorts of statements, again, I have to put geometric constraints on my open book decompositions. In 3 manifolds, I don't. Right? This is sort of a purely topological data. So the standard thing to say is that, well, Giroux reduces the study of contact structures to these sort of simple surface and homeomorphism, diffeomorphism pair. While that's true, it's also, one has to keep track of these stabilizations. Stabilizations, though I haven't defined them, they change both the diffeomorphism type of the surface, they move you into a whole new type of mapping class, et cetera, et cetera. So of course the complexity is still there. It's just in some sense compartmentalized. It's broken up in some way, reorganized. Whatever your viewpoint on this, though, the Giroux correspondence theorem has played a huge role in what has happened since then and led to a wide range of developments and work that's still going on. So the idea to the rest of the talk is to, as I said, survey those, looking at sort of a selection that I find interesting and that contain in particular open problems, recent progress, things like that. Okay, so now we get on to our survey of applications. This is our end of our introduction. Questions on anything? I'm going quickly. Anyways, feel free to shout out if you want. Okay, so the first stop on our tour is going to be one of these sort of very easy to pose, but very sort of frustratingly difficult to answer questions. And that concerns the support, right, larger. Genus of a contact structure. So the support genus of a contact structure sort of takes the view of looking at the correspondence and saying, well, since I have this equivalence class associated to a contact manifold, can I say something about the equivalence class, thereby defining a contact property that I might not have known about much. If you're familiar with it, the way the Heegard genus gives you a smooth manifold invariant. I can look at all the Heegard splittings, which has the smallest genus. That's something interesting. So I can do exactly the same thing over here. I can just look at all the surfaces involved in a stabilization equivalence class and ask for some sort of bounds on their topology. So in the Heegard case, the genus is the only thing that you have to play with. Here, of course, it's a surface with boundary, so you can ask about either genus or number of boundary components. Once I finally tell you what stabilization is all about, you will see quickly that the number of boundary components can always be made whatever you want it to be, so that's not so interesting. The genus, on the other hand, is seemingly quite interesting, so let's give you a definition. So this was due to Etchener, who first wrote it down, I think. The support genus C, so we put SG of a context structure. So this is just what I said. It's the min of the genuses where S is a page in some open book supporting. So fairly straightforward concept. So Ednar showed very quickly in the same paper, so this is in 05. So here are some things that are known. So Etnar tells us that if my context structure is something known as over-twisted, then I can always cook up a planar open book decomposition for it. So I'm not going to give you a proper definition of over-twisted. The way you should think of over-twisted context structures, if you've not seen one before, they are the geometrically non-interesting ones in some sense. If you're going to have any interesting geometric property, you cannot be over-twisted. That's in some sense how they're defined. They are, I guess a better way of saying it is that they're completely determined by the homotopy class of their underlying plane field. So they're all classified by algebraic topology from a long time ago. So this is in some sense a good result, right? Because it's telling us that this invariant we're cooking up here might have some geometric significance, what we would like. And indeed, Ednar found that there exist context structures such that the support genus is greater than 0, i.e. there are obstructions. The obstructions that Etnar found had to do with looking at symplectic fillings of these things. So specifically, I'm not going to write it down, but just for the interested, the idea is that if we have a symplectic filling of a context structure and it's planar, then that filling should, on the one hand, only have one boundary component, and on the other hand, its intersection form should be negative definite. So it's given those, it's very easy to cook up examples of things that have support genus greater than 0. So this was then, I'll say, extended by a bunch of people and in a bunch of different ways. So first, Osvath, Stipschitz, and Szabo came up with a slightly different obstruction. This was in 06. I came up with one in 2012, and then the group of Paolo Gugini, Marco Gola, and Olga Plamenovskaya. More recently, in 2020, came up with, yet another. So the reason for writing all this up isn't just to get my own name on the board, but it's to kind of indicate this a wide range of techniques that have gone into this, which make what's unknown even more surprising. So as I said, Ednar was looking at symplectic fillings. Oswald Stipschitz Szabo, of course, looking at Heegard-Floer homology. I was looking at certain monodromy factorizations of Stein fillings. This last crowd took it from a more algebraic geometric viewpoint, and we're looking at Milnor fibers. So all sorts of different ways of looking at it. And each of these results are independent of the others. None contain any other one. Each one obstructs something that the others can't. So with all of this, though, what's incredibly frustrating is that none of this work has managed to uncover a single contact structure with support genus greater than 1. So unknown. And so you might say, well, looking at this, well, I mean, being planar is a very particular thing. Maybe it's just a dichotomy. Maybe all the other ones are 1. I don't think that anybody who's thought about this for very long thinks that. One fairly good reason is the existence of potential examples of these. So let's say they exist. I will call them potential examples. And just so that you leave with something, let me give you some examples to play around with. Suppose I have a surface of genus G, and it has 1 boundary component, where G is, I guess, bigger than 1. And I want to look at the mapping class, which is a single den twist around a curve parallel to its boundary. So let's draw a picture of that. So there's my surface of genus G, 1 boundary component, and I have a little twist there. And so again, I'm just cutting along that, twisting 360, gluing it back together. I claim that this has support genus G. Of course it does. How could it not? Right? But I don't have a proof for it. What's the intuition behind it? And this gives me a opportunity to tell you what stabilization is all about. So I thought it would be worth sort of talking a little bit about the intuition. So why does this have support genus G? Well, if it didn't, I should be able to find somewhere in my stabilization equivalence class some other open book decomposition that has some genus G prime, has some number of boundary components, and has some monodromy. I don't really care what it is. And what Giroux was telling me is that I can stabilize, 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 and find some common stabilization. So I can stabilize, 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 destabilize, 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 and get to that guy. So what is the stabilization all about? Well, to stabilize it, all you'd have to do is you add 1 handles to your surface. And then, actually, let me get a color for this. So rather than write it down, I'm just going to give you a picture. So here's stabilization. I'm adding, all the blue stuff is stabilization. I'm adding a 1 handle. And then I'm taking some simple closed curve, the only constraint on this curve being that it crosses the 1 handle exactly once. And then it goes and does whatever it wants to in the surface, and it comes back. And so what I want to do is, again, add the 1 handle to my surface. So my surface is changing, and I want to compose the existing monodromy, which here was just a den twist around the boundary, with a den twist around this red curve. Hopefully that's fairly clear as a procedure. And so I can continue this. I stabilize, I stabilize, I stabilize. I get up to this point. And so when I'm there, what do I have? Well, I still have this surface. It still has its twist around what was its boundary. And then it has a lot of 1 handles attached, a sort of structure out there. And those 1 handles are such that each one, when you add it on, again, it has this property that the curve goes once over the handle, then it can do whatever else it wants. So once I'm up to this point, the question is, how can I destabilize in a way that sort of destroys the genus over here in any possible way? And if you start to play with this, I would encourage you to do so if you're interested. Try to understand what it means to be destabilizable. In some sense, if I want to destabilize something, I need to be able to find some co-core of an arc. The co-core of the arc needs to be something that under that monodromy is sort of sent to one way, never comes back, and then comes like that, has no intersections in the middle. And so if I find such a thing, it seems pretty clear from what I've said that at least for the first destabilization, it has to be in this added on part, because any arc that goes and crosses this and comes back couldn't have this property. Again, a lot of hand waving here. And it seems that as you continue to do this, each additional arc must also have that property. I would hope that this leads to some sort of proof. I've never been able to make it work out. I know a lot of other people have thought about it. But it's the kind of sort of hands-on thing that you can play with and see if you get anywhere with it. But anyways, it's this very sort of frustrating phenomenon that I wanted to include as part of the talk. Any questions about that, Mark? The identity, could you make that? Well, the identity would just give you some copies of S1 cross S2, and we know that's planar. Anybody else? The point is, the twist does, what I was saying about looking at these cocores, the point is that the cocores would have to sort of cross the twist and then come back. Right? If there was no twist, then that wouldn't be. Anybody else? Okay, so I want to shift focus here. This was kind of just an aside. And what I'd like to do for the rest of the talk is kind of look at the contrary question. I look at properties that are known to have some geometric significance and ask how they reflect over in this equivalence class. So to do that, let's just let P be a property of a contact structure. What do I mean by this? I mean Stein fillability. I mean boundary of a left shift variation, something that we might be interested in over in a contact structure. So we can ask a couple of questions. The first question we could ask is a fairly wide-ranging question. It's, well, can P be detected in an arbitrary open book? So this is kind of the holy grail of these types of questions. We don't have a lot of answers to this, but if there's time, which there looks like there probably won't be at this point, I would like to talk about some ongoing work towards resolving this for a number of properties. A sort of more limited question, if we pick a surface, like a diffeomorphism type of surface, associated to that is a mapping class group, fairly famously, well studied by Thurston and others, has a lot of algebraic structure. So this is just the group consisting of all possible monodromies of open book decompositions that have that surface as a page. And so if we look at that just as a set, let me write it down. So the ones that follow, so within that mapping class group, I want to consider the following set. I want to look at all the ones which support contact structures that satisfy my property. And I can ask what kind of structure this has. So naively, you might ask, hey, is this a subgroup of any sort? And you would immediately see that, well, no, the minute inverses are allowed, everything becomes over-twisted. So that's not what we want. But we can ask if this is a monoid. So while this might seem like a slightly odd question, it's actually quite natural in light of a theorem, which is due to Baker, Etnayer, and Van Horn Morris in, I think, 2010, which was also, we should put Baldwin, also sort of implicitly come up with this result. It's more of an observation, really, once you have everything set up properly. That the answer to question 2 is yes, if and only if the property you're interested in is preserved under what's known as Stein cobordism. So what's a Stein cobordism? Just for the unfamiliar, a very quick overview of this. So Eli Ashberg has a famous classification, or what's the word for it, characterization of Stein domains. And in dimension 4, what this says is your Stein domain, if and only if, as a 4 manifold, you can be built up with a 0 handle, which of course just sits in C2, has a Stein structure from there, arbitrary 1 handles, and then 2 handles that are added in a particular way. So the framing fits with the contact framing that you got as the contact tangencies. So what this is saying is exactly that. Is P preserved under adding arbitrary 1 handles and 2 handles with this framing attachment, i.e. the trace of that operation, that 4-dimensional operation. Now, to sort of strengthen this dictionary between contact geometry and open book decompositions, and to give the setting in which this theorem was actually proved, what this equivalently means is that it's preserved under adding 1 handles to the page and composing the monodromy with positive bend twists. So these are the open book decomposition versions of those 2 statements. So if you can show that these 2 things are true, then you're a monoid. Really, of course, one doesn't care if you're a monoid or not. One cares if you satisfy these conditions. So in some sense, being a monoid is just shorthand for you are preserved under all the nice operations we'd like you to be preserved under. Good. So look at a few examples of these and how they fit together. So what are some relevant monoids? Well, starting with properties we've already looked at, one can look at the property of being the boundary of the Lefschetz vibration. As I had discussed when we were looking at this, if you're the boundary of a Lefschetz vibration, then the compatible open book comes along with a factorization into positive den twists. And indeed, the opposite implication is true. So this leads to a monoid, what we call den plus of S, i.e. this is everything that can be factorized into positive den twists. That it's a monoid is completely trivial, right? I put 2 positive words together, I get a positive word. So that's great. Slightly more geometrically interesting, we noted that these Lefschetz vibrations carry the structure of a Stein domain. The contact structure on the boundary is compatible with that with the complex structure that that gives you. So we can consider the monoid of Stein fillable contact structures, those that arise as the boundary of Stein domains. So that is a monoid, one has to check that it's preserved under Stein-cobordism, which of course it is by definition, but we should put up Eli Ashberg's name because he's the one who worked all of this out back in 90. So of course 90 is before 2010, so he didn't say anything about monoids because we didn't have Giroux's theorem and so on, but he again showed that all these conditions hold. I'll say something about whether or not the inclusion is strict in a moment. Let me just write up the rest of these. We can weaken this a bit further and ask about symplectically fillable things. This one, Weinstein, at about the same time, 91, work out that all those things hold. And then we can finally get to kind of the bottom of the monoid barrel here and ask about tight structures. So tight structures are those which are not over-twisted. And even though I didn't give you a very good definition of over-twisted, hopefully it was enough to show you that the tight condition, it's a somewhat mysterious condition, but anything, as I said, that's geometrically interesting has to sit in tight. And so that this was a monoid was then shown by myself in 2015, resulting in a Frontiers of Science Award, which I proudly display in my office. I should say, though, that this was very much a proof that worked with open book decompositions. So up here, we weren't really thinking about open book decompositions at all. This is very much a property of open books. This one, again, a very sort of strongly open book related result. So let me tell you in the few minutes I have left here, some knowns and some unknowns. Well, so when I say it's a monoid, what I mean is that I've confirmed that it satisfies these conditions. That's one of the unknowns I'm coming to. Exactly. So, right, there's the question of sort of identifying things, and there's a question of detecting them. But very quickly, let me just go over what's known about these inclusions. So there was a well-known question due to Giroux back when all of this came together, who had asked, had he conjectured, it's not really clear, whether or not Den plus and Stein were in fact the same thing. I should put an S here because that actually becomes important. So this was sort of an interesting question for a while. Again, it kind of, if you want to play around with stabilizations, you can come up with some reasons for or against. Finally, in 2009, Chris Wendell, using a pseudo-holomorphic curve operation argument, was able to show a slightly more general result, but implied that the answer to this question is yes, if S is planar. So that was very interesting and sort of led to a lot of research and new results. In 2010, myself, and then soon after the group that I've written their names up here, so I'll just abbreviate them this time as BEEHM, showed that the answer was no in general, i.e. there exist surfaces of higher genus for which that's not, the monoids differ. And then there was some more work on this in the intervening years, and 14. Liska did some work on it. And then finally, I just wanted to mention it because it's sort of a recent result. Just last year, myself and Vitaly Brezhevs, my former student, showed that the answer is in fact no for all non-planar. Okay, so this is sort of the sort of questions that we're thinking about. So that gives a sort of a full answer to Giroux's thing. I won't say anything about how that goes. I just wanted to have it up there. It's also known, I should say, that all the other inclusions are known to be strict. That's a result of Gagini in 2005. So if you get the right S, at least. Okay, the last thing, I only have a couple of minutes before it's supposed to end here, but I want to address András's question a little bit. That's sort of the ongoing research part I wanted to talk about. What's unknown is how to detect membership in any of these things. So, I mean, if we're looking at them in Den plus, if I hand you a monodromy, it's no easy task to work out whether or not it conclusively has a positive or negative factorization. So there are some obstructions to this, right? You can check that the associated contact structure isn't in one of these things. That would do it. But just from a purely sort of mapping class point of view, this is very difficult to do. In certain circumstances, you can. I won't have time to say anything about that. Again, these, really nothing. Now in tight, as part of my work on this, I came up with a characterization of tightness in terms of open book decompositions. It has the problem, though, that to properly detect it, you potentially need an infinite amount of data. So there's no finite algorithm that allows you to do this. Sort of trying to fix all of this is the subject of ongoing work with, I'll write up a few words. What we call it is the spectral order of a contact manifold. So this is due to Kutluhan, Gordana Matic, Jeremy Morris, who's featured on the board several times, and myself. So this is an ongoing project. It's been ongoing for the last 8 years or so. About 8 years ago, we released a paper giving sort of the very basics. About 5 years ago, a further paper giving the full theory. And then earlier this year, a paper explaining how you can do some of the calculations a bit more easily and reduce some of the calculations to finite ones. So very, very cartoon introduction to spectral order. It's supposed to be some invariant of a contact structure that tells you loosely where you sit in this. It's supposed to be computable. It's supposed to associate a number to the contact structure. The way it works, just in, again, cartoon fashion, it's very much something that comes out of open book decompositions. So I start with what I would call an augmented open book decomposition. So I have my usual open book decomposition, and I put in it a bunch of properly embedded disjoint arcs. So this is the data I start with. I would like there to be enough arcs to cut the thing into a disk. I might actually need more than that. That's where the difficulties lie. So Oswath and Szabo, given to this, of course, from this data, let me say it that way, can build up a chain complex associated to their Heegard floor theory, which I'm just going to call CF hat of that information. So this is, if you're used to Heegard floor theory, this is just the chain complex of the hat version of that. So this, though, is, since I've specified a contact structure implicitly, because I've started with an open book decomposition, sitting in this complex is a particular class, the contact class, vanishing of which gives me some information about the contact structure. If the contact structure is over-twisted, it vanishes. If it's Stein-fillable, it doesn't vanish. It doesn't give me any further information than that. So what I should also say, actually, just to be clear about this contact class is something that you could also have put in my monoid tower over here, sitting between Stein and tight. You could have the monoid of things whose contact class does not vanish. And that would actually have the unique property among all of these things is that it's something you really can calculate. So it's a very, very useful tool. So what we do is we sort of augment this, turn it into a filtered complex that I'll just call super fancy CF of all this stuff, from which we can extract what we call a Heegard floor spectral sequence. And then we can ask, well, if I try to track the contact class into the spectral sequence, how long does it persist? And then that gives me the number I'm associating, not necessarily to the contact structure, but to this original data, which is at what page does it die, if it dies. It could be infinite. So a priori, this is just a invariant of this data. So let's define, I'm going to say little o of the data to be page on which C vanishes, if it does. And so we can then define, I'm almost done. Let's try to do this really quickly. A contact invariant, the spectral order of the contact structure. So that should be the min of O of all this data over all possible data. So from that point of view, it looks like something you could never possibly calculate. The main theorem, though, is that for every open book decomposition, there exists an arc collection such that O of this data is O of the contact structure. So you can always do it. What you don't know is how big you need to make this. We have been able to show recently, that's the last thing I'll say, this is in the last paper we put out, that we can, at least through a finite process, determine if something is at least finite, not infinite. So that gives you an effective obstruction to being Stein fillable, that is, can obstruct things that no other method at the moment can do. That's at least something along these lines. Okay, I'll stop there. I'm over time. Thank you very much.
Let's thank Andy for an nice talk.